So we've learned about how stars form and how they evolve over their life cycles. And today we're going to talk about one of the possible outcomes for the end of a star's life. So today is going to be all about black holes. So today we'll be talking about black holes, and this is an artist's representation of what a black hole might look like. Towards the end of the lecture, we'll see an actual picture that we've taken of a black hole. So I'll be sure to point out when we're looking at real images or data versus when it's just an artist's representation. So to review, depending on the mass that your star had during its life, it will determine what it ends up with at the end of its life. So if it's a low mass star, so similar to the mass of the sun, it will end up as a white dwarf where it will not, the self-gravity of all of its mass will not be great enough to overcome the electron degeneracy pressure, and so you have a bunch of carbon atoms with their electrons getting squished into the smallest possible state, but not enough mass to continue pushing it further. If you get a higher mass star, say 8 and above solar masses, then you're getting into the region where you can overcome this degeneracy pressure, and it'll be an iron core instead of a carbon core, but you can overcome this electron degeneracy pressure and you can force the electrons and protons in your atoms to start to fuse. And so when protons and electrons fuse, you get neutrons, and so all that will be left in the core of the star is a bunch of neutrons. But neutrons also have a degeneracy pressure, and so as long as you don't exceed that mass, as long as you don't have too much mass to exceed the neutron degeneracy pressure, then they can kind of support their own mass against gravity. And that mass is about 3 solar masses. Then, if your core exceeds 3 solar masses, we don't know of any other physics to support that gravity, and so you'll just collapse into a black hole. And so if we can remember what branch of physics governs all of these degeneracy pressures that supports the neutron star and the white dwarf. Yeah, so these are quantum mechanical effects. So electricity and magnetism are 2 sides of the same coin that we'll see later. So that would prevent 2 electrons or protons from getting too close together. But we are past that phase, and we're in the realm where quantum mechanics is the only thing that can keep the white dwarf and neutron star in shape and not collapsing. And then thermodynamics does have a type of pressure that's just heat or radiative pressure, and that's at a much larger scale. Black holes are really the ultimate victory for gravity in this battle between the inward force of gravity and the outward force of radiative pressure that we've seen in stars. So we'll talk about what a black hole is, what it would be like to visit a black hole, and then how do we even detect these objects. So this is an artist's representation, and these are kind of the key features of a black hole. So first, a black hole is going to be a spherical object. So it's not really a hole, that would just kind of be a circle. But if you think about what was the progenitor of this black hole. It was the core of a star, and that's a spherical object. So a black hole is really a sphere, and maybe we'll start from the center and work our way out. So the center of the black hole is perhaps the most controversial area, because this is really where our physics breaks down. So we have quantum mechanics, which tell us how things in very small regions behave. And then we have general relativity, which tells us how things with mass behave. And at the center of a black hole, those two physics don't agree with each other. So one of them, or both, either one of them is right and the other's wrong, or they're both wrong. And for the last 100 years, we haven't been able to reconcile those differences. So this is something, if you can figure out how to make general relativity and quantum mechanics play with each other, then you would get a Nobel Prize, probably. Then, going out from the singularity at the center, you get the event horizon. So this is the outer boundary of the black hole. So if you're outside of the event horizon, you're not in the black hole. Inside the event horizon, you are in the black hole. And it's not like a surface, it's just the region of space outside of the black hole is where you could potentially still escape from its gravitational influence, but if you're inside the event horizon, not even light can escape. And light is the thing that travels fastest, so if light can't escape, then you certainly can't escape either. Then the next region out from there is called the photon sphere. And so this is basically where, if you had the speed of light, that's the orbit that you could have around the black hole and not fall into the black hole. But light is the only thing that can travel at the speed of light, so these are just photons that are at that radius. Then you have the innermost stable orbit, so this is where matter could be orbiting the black hole without falling in. You have an accretion disk, which is all the matter that's orbiting the black hole, and then some black holes will have these relativistic jets, and that's a consequence of conservation of angular momentum. So if you think about some of this stuff that's orbiting the black hole will fall into the black hole, but if I start from an orbit that's really far away from the black hole and I start falling in towards the center, some matter will fall into the black hole, but some matter will just be ejected out of the system along these relativistic jets. These jets are powered by magnetic fields, but those magnetic fields are generated in the accretion disk, and so they're aligned with the rotation of the black hole. So as soon as something crosses the event horizon, we have no way of getting any information about that object. So there's this kind of an interesting, parallel. So there's the speed of light, which is how fast a photon travels, but there's also this idea of information. So the fastest way that we can transmit information is with light. So if something were to fall into the black hole and we wanted to, let's say we sent a probe into the black hole and we wanted to get data out, there's no way to send that data out because light is the fastest way to get information out, but no light can escape the black hole. So we really have no idea what is going on past the event horizon of a black hole. We have our physics theories that try to explain it, but like I said, as you get to the singularity, that physics breaks down. So it's very hard to say what exactly is going on in there. But yeah, that's because there's that uncertainty. That's where you get crazy theories like, is a black hole like a wormhole? Could you use that to tunnel to a different part of the universe or something? So you get some really interesting but hard to justify in theory ideas. So what even is this black hole? So it's just an object that is so dense and has so much gravity that the escape velocity is greater than the speed of light. So light can't even escape from inside of its event horizon. And this is the end result of some massive stars that go supernova. Their cores get so massive that they collapse into what are called stellar mass black holes. And again, this is an artist's representation of what that stellar mass black hole might look like. And you can already see some weird stuff happening around the edge of the black hole, and we'll come back to that in a moment. So it turns out there are two main categories of black holes. There are stellar mass black holes, which we think are generated from the death of massive stars, and those have at most hundreds of solar masses. But then there's this other class, supermassive black holes, and these have up to billions of solar masses. So completely different scale compared to the stellar mass black holes. These we typically find in the center of galaxies, and we'll talk about those when we talk about galaxies in a couple weeks. So let's review. Escape velocity is just to derive it, we can set the kinetic energy equal to the gravitational potential energy, and this is what those formulas reduce down to. And if you wanted to turn the Earth into a black hole, for example, you would set the escape velocity equal to the speed of light, and then if you do that calculation, the radius of the Earth would go down to about 1 centimeter. So you'd have to shrink the Earth all the way down to 1 centimeter in radius in order for it to act like a black hole. So the Earth is very far from being a black hole. What happens to the escape velocity for an object if you keep shrinking it? Yeah, so if you keep shrinking the size of the object down, then you'll increase its escape velocity. And so earlier in the semester, we actually derived the radius of a black hole. You set your escape velocity, or you start with your formula for escape velocity, and then you set the escape velocity equal to the speed of light. You do some rearranging to solve for the radius. And then once you've done that algebra, you get that the radius is 2 times the gravitational constant times the mass divided by the speed of light squared. And so this is the radius of a black hole for a given mass. And this is called the Schwarzschild radius. And this is the radius for a non-rotating, neutrally charged black hole. And it turns out if you take a general relativity class at some point in the future, you can do a much more rigorous derivation, and you end up with the exact same formula. So we got it just by doing kind of introductory physics, but it turns out when you do it with much more complicated physics, the result ends up being the same answer. So there's not really a surface of a black hole in terms of something that you could stand on, but this barrier between basically the inside and the outside of the black hole is what we call the event horizon. So that's, if you're outside of the event horizon, then you could potentially have enough velocity to leave the black hole, like the region of the black hole. But if you've passed the event horizon, then your escape velocity would be greater than the speed of light, and so there's no hope you have for escaping. And that the radius of that event horizon is the Schwarzschild radius for this type of non-rotating, neutrally charged black hole. But that, obviously, I've said some very specific words there, so that would imply that there are black holes that rotate, and so everything in the universe is basically rotating, right? You start with your gas cloud in space. As it compresses and starts forming a star, it starts to rotate. So stars are rotating, and black holes, at least the stellar mass black holes, are starting from a star, so that object is going to be rotating as it forms a black hole, so the black hole is going to be rotating. So that the radius of a rotating black hole is the Kerr radius. We said that that was for a Schwarzschild radius, it was a non-charged black hole. That implies you could put charge onto a black hole. This is related to the conservation of charge that you have in electromagnetism. So you can't create or destroy charges, and so if you have a bunch of charged particles falling into the black hole, then the black hole will assume those charges. So if I had a neutrally charged black hole and then an electron fell into it, now my black hole has a negative charge to it. And so the radius of those charged black holes is the Reisner-Nordström radius. And then, of course, a black hole could be rotating and charged. And then its radius would be the Kerr-Newman radius. It turns out that the Schwarzschild radius is the largest radius of the black hole. So it's a good approximation to make. If you start adding rotations and charges, you end up just making your black hole smaller. And so what is the size of a stellar mass black hole? So turns out it's pretty similar in size to the neutron stars that we were talking about last class. So the event horizon for a 3 solar mass black hole is just a little bit smaller than the radius of a neutron star. So about the size of a small city. And so again, this is the radius of the event horizon. So anything outside of this event horizon might not fall into the black hole, but anything that's past the event horizon is stuck in the black hole for potentially the rest of time. So that brings us to now talking about how does the mass of the black hole influence the stuff around it. So when we start talking about space, we're not just going to talk about positions, but time and space are going to be kind of intertwined with each other. So this is a representation of a flat space-time, and in a flat space-time, if you have a photon, for example, it can just travel in a straight line, and that's what we expect a photon to do. But as soon as you start introducing mass into your space-time, you're going to curve your space-time. And so now, if I look at this kind of inner circle around this mass, now I could emit a photon, but if it's along this circle, now it'll start to orbit this mass. And so now my photons don't necessarily just travel in a straight line, they travel along curved paths, and those paths are, the curve of those paths is determined by the mass you have in your space-time or in your universe. And this is Einstein's theory of general relativity. So this is a separate way of thinking about gravity than what Newton had. In Newton's theory of gravity, there would be no reason for a photon to travel along this curved path. So photons don't have mass, so they shouldn't be influenced by gravity according to Newton. But Einstein says because their photons travel through space-time, if that space-time is distorted by mass, then that can influence the path of the photons. So this is just, you could say, like a planet or maybe a star mass warping the space-time. And you can think of a black hole as the maximal warping of space-time that you could get. So the event horizon is down here, and this kind of just stops at the event horizon because, again, we don't really know the physics very well of what's happening inside of the event horizon. According to general relativity, everything should get crushed into a singularity inside of the black hole, and that would represent kind of an infinite density or an infinite distortion of space-time. And once you are in the event horizon, then you would need a speed faster than the speed of light to escape, and therefore nothing is, once it's inside the black hole, nothing is getting back out. And we talked about this earlier. If, let's say, you put a probe into the black hole to try to get some data out, because that data would have to travel faster than the speed of light to get out, you can never get any of that data from inside of the black hole. But the stuff that falls into the black hole does have consequences to the black hole, in that the black hole's mass can increase. If you have charged particles falling into the black hole, then the black hole will obtain those charges, and then angular momentum is going to be conserved as well. So if you have a bunch of rotating objects falling into your black hole, then the black hole's rotation will change based on the things that fall into the black hole. So there are still laws of physics that are being conserved, like mass, charge, and angular momentum, but we lose information about the things that fell into the black hole. So in the center of the black hole, we don't know of any forces that can stop the inward pull of gravity. And so in theory, that would mean that everything that has fallen into the black hole should exist at a single point in space called the singularity. But this is where the quantum mechanics and the general relativity disagree. So when we talked about the mass limit of a white dwarf, we said that if you increase the position that you know an object is in, then you have to increase the velocity that it's moving at. And that was the Heisenberg uncertainty principle. So the same principle should apply to the singularity. We're now putting tons of mass all in a single point, and so that would make your velocity absurdly larger than the speed of light. And our physics says that's not possible, and so quantum mechanics says there's no such thing as a singularity. So this is the disagreement between quantum mechanics and general relativity in the center of this black hole. Okay, so I'll give you guys a moment, a minute or two to think about these questions. So, do black holes gain mass? And maybe think about the consequences if they do. And then, can black holes ever lose mass? And what would those consequences be? So, feel free to talk amongst yourselves, and then we'll come back together and share. Okay, so what do people think? Gain mass, yes or no? Yes? Okay. What about lose mass? So most people say no, some people are unsure. Okay, so everything that I've told you should lead you to believe that they can't lose mass, but we'll talk about some weird stuff in a second. So, gaining mass, yes. Everyone seems to get that one. And as matter falls into the black hole, its mass is going to increase. And this increasing mass actually does have an effect on the black hole, in that the more mass you have in your black hole, the larger your radius is going to be. So if I increase the mass on the right-hand side of the equation, I have to increase the radius on the left side of the equation, because everything else on the right side of the equation is just a constant. So the more mass you put into your black hole, the bigger it's going to get. But now let's learn a little bit about quantum mechanics to see how maybe our black hole could lose mass.
Quantum foam, presented by Science at NASA. Quantum foam. It may sound like the name of a new craft beer, but it's something even more amazing. To see it, you have to dive down the rabbit hole of quantum mechanics, a branch of physics that describes how light and matter behave at atomic scales. In this bizarre realm, matter can be in two places at once. Electrons can behave as both particles and waves, and Schrödinger's cat can be alive and dead at the same time. Or so the quantum theorists tell us. Theirs is a world wildly different from Einstein's. In his highly successful theory of general relativity, Einstein tells us that energy equals mass, and mass warps space-time. Remember the physics analogy of the trampoline with a bowling ball in the middle? Like that ball, which gently distorts the trampoline's canvas, the sun warps the smooth canvas of space-time enough to make planets move in curved orbits. A whole galaxy warps space-time much more. The more massive the body, the more warping. But if we could zoom in on the quantum realm, we wouldn't see a smooth expanse of canvas gently distorted by massive bodies. We'd see quantum foam. Quantum gravity models predict that space-time is a seething foam of tiny regions where minuscule new dimensions unfurl and then furl back in on themselves, spontaneously appearing and disappearing with inconceivable quickness. These regions blink in and out of existence like the bubbles in the foam of a freshly poured beer. There's no such thing as empty space. There is only quantum foam everywhere. Such is space-time for a quantum physicist.
In that quantum foam is where we're going to find the answer to how we could possibly lose mass from our black hole. So we've talked about the Heisenberg uncertainty principle, and it turns out there's different versions of that. So we've seen the one for position and momentum, where this didn't allow us to exceed a certain mass for our white dwarf and caused it to blow itself apart if we made our position uncertainty too small. It turns out there's another version of the uncertainty principle for energy and time. And it has similar consequences, so the better you understand something's energy, the least you're going to understand the amount of time that it can have that energy. Or if you make your slice of time very small, then your energy uncertainty can start to become very big. And so what this means and what they were talking about with the quantum foam was that around the black hole, there can be, if you take a short enough slice of time, you can get a large enough energy uncertainty that you can spawn what are called virtual particles. So these will be so these are the positive and negative energy particles that are in this diagram. And if there was let's pretend there's no black hole around, these positive and negative particles are always popping in and out of existence in the universe, but they very quickly recombine with each other. So the delta T is very small, and so there's enough free energy to make these particles, but the positive and negative energy particles, when they hit each other, just annihilate, and so they're popping in and out of existence constantly, but they're not really changing the overall energy of the universe. So they're basically like some energy is created, but then it's immediately destroyed, and so there's no conservation of energy violations going on. So that is fine if you're just kind of out in space and there's nothing near you. But these pair productions if they're happening near a black hole, there can be some pretty profound consequences. So you could imagine a positive and a negative energy pair spawning right near the event horizon of the black hole. And some of these negative energy particles are going to fall into the event horizon, and the positive energy particle is not going to fall into the event horizon. So there's some complicated physics for why the negative energy particles are more likely to fall into the black hole than the positive energy particles. But all we need to know is the negative energy particles are the ones that are more likely to fall in. And so when you combine a negative and a positive energy particle, you're going to lose mass, basically. Because these little particles will have mass, and when you combine positive to negative, you erase the mass, basically. So if these negative energy particles are falling into the black hole, then they're basically taking away mass from the black hole. And so this process is called Hawking radiation, named after Stephen Hawking, who's the person who came up with this idea. And so the consequence for this for black holes, if there's no mass falling into the black hole, you just have a black hole kind of by itself out in space, then over time, this process of Hawking radiation will lead to the negative energy particles falling into the black hole, and eventually the black hole is going to lose all of its mass. But this is something that happens over timescales of longer than the universe has currently existed. So when we talk about the eventual fate of the universe, we'll come back to what this is called. This is black hole evaporation. And so there is a mechanism that could cause your black hole to lose mass. But it's something that would take a very long time to happen, and any black hole that has like an accretion disk and has matter around it, is going to be gaining mass at a much greater rate than this evaporation would take the mass away. Yeah?
Didn't this get disproved by Leonard Susskind?
That I do not know. But this is definitely has not been proven. This is a theory as to what could happen. And we need a lot more observations of black holes to be able to prove or disprove the things that are happening around them. But yeah, this is everything that we're, not everything, but almost everything that we're talking about with black holes is theoretical. So there's lots of room for interpretations, and if you are interested in astronomy and physics, this is very active areas of research. So this is just a scene from Interstellar. If you haven't seen it, it's a good movie. All of the visuals, of course, are computer generated, but they worked with prominent astrophysicists to develop these computer graphics. So this is kind of, according to an astrophysicist, what being near a black hole might look like, and if you had the money of a movie studio to actually make a simulation to show people. So and we'll talk about some of the physics that comes up in what the people say during the scene.
Detach!
Goodbye, Tars.
Goodbye, Dr. Brent. See you on the other side, Coop.
See you there, Slick! Okay, Case. Nice reckless flying.
So what they were doing in that scene, we've kind of talked about earlier in the semester when we talked about how we send probes out into the solar system. So they were basically doing a gravity assist. So they ended up in space too close to this black hole, and in order to get away from it, they were going to use the black hole itself to gravity assist their way out away from the black hole. So they were they weren't in the black hole yet, so they could still escape if they generated enough velocity, and so that's why they were firing their thrusters and ejecting some of their excess mass to try to get enough speed and then use the angular momentum of the black hole itself to kind of slingshot their way out of this system. And one of the interesting things they said was that this maneuver is going to cost us 51 years. So what did they mean by that? So because the black holes have a lot of mass, and mass distorts space-time, the closer you get to the event horizon, the more your time is going to be messed with. So if you stay far away from the event horizon, your time is going to pass normally, but the closer you get to the event horizon, your time is going to be dilated. So the time that you experience, or your clock, is going to tick at a different rate than the people who are not near the black hole. So by them going so close to the black hole, from their point of view, their time passed normally, but from the point of view of the people on the Earth, that them going so close to the black hole, basically the people on Earth would have aged 50 years to their 10 minutes or whatever it took for them to do their little gravitational slingshot. So time passes more slowly the closer you get to the event horizon. And so this is the general relativity consequence of that. You also have special relativity consequences where the closer to the speed of light you get, you also get a time dilation. There are other consequences of having this very dense mass distorting your space-time. It's called gravitational redshift. We'll come back to talking about redshift when we talk about the evolution of the universe, but if you have, let's say, the space between these two objects, if there was no mass, then the distance would just be kind of a straight shot. But if these objects have a lot of mass, then the space-time is getting stretched by that mass, and so the wavelength of light that you have is getting stretched. And so this is gravitational redshift. So for example, the sun doesn't have a lot of mass, but any photon that's leaving the sun is going to be redshifted as it climbs out of the sun's gravitational well. And so this is something that we can measure on the Earth even. So this is one of the ways that we verify general relativity. We've talked about tidal forces before. So tidal forces are what cause the tides on the Earth and what cause certain objects to be, their rotation to be locked as they orbit an object. And black holes have a lot of mass, and they will also exert a tidal force. So if you're falling in towards a black hole, your feet are closer to the black hole than your head is, and so your feet will feel a larger gravitational pull than your head, and so you'll start to get stretched out by this tidal force. This is called spaghettification because you're basically turning objects into long strands like spaghetti. It turns out that the spaghettification is worse for stellar mass black holes than it is for supermassive black holes. So for a stellar mass black hole, this tidal force would be great enough that you're probably not going to even get to the event horizon alive. So you'll be stretched apart before you pass the event horizon. But for a supermassive black hole, the event horizon is so big that this tidal force is not really that great until you're already inside the event horizon. So if you ever did want to try to go into a black hole and be alive when you got there, then a supermassive black hole would be your best bet. Not that I would recommend anyone trying to go into a black hole. Okay, so how do we know that these things are there? They're too massive for any light inside of them to escape. So we have detected them directly, which we'll talk about later, but we also use a lot of indirect evidence. So if we find something orbiting a region of space and it's moving very quickly, such that the object it's orbiting has to be greater than 3 solar masses, but we don't see any light from that object, like it's not emitting light like a star, then that would lead us to believe that the object being orbited is a black hole. And so these black holes can be in a binary system. So just like the neutron star and the white dwarf can steal matter, so can the black hole. And these accretion disks around the black hole are very hot. They emit X-ray radiation. And so the black hole in a pair with a star can be an X-ray binary. And there's likely an X-ray binary in the constellation Cygnus. And we also have now taken direct images of a black hole. So this is the black hole in the center of a nearby galaxy. So this is a supermassive black hole. And these images are taken with radio data. And when we talk about galaxies in a couple weeks, we'll come back to how we make these images for these supermassive black holes. Quasars, or quasi-stellar radio objects. So when these were discovered, they were objects in space that emitted radio light, but didn't emit any other kind of light, and they were point-like, so they were not like a galaxy or something. So they were quasi-stellar because they were point-like and they emitted radio, so they were radio objects. At the time, they didn't know what these were, but now they know that these are black holes with jets coming off of them. So they don't pulse like a neutron star does because the rotation axis and the jet are always aligned. And the magnetic field for this quasar doesn't originate in the black hole, but it originates in the accretion disk of all the material that's around the black hole. And that's why the rotation and magnetic field axes are always aligned. So just the reminder of all the different parts of the black hole. And then just to summarize, so black hole is a massive object, and it's so dense that not even light can escape from its event horizon. And a common misconception people have is that black holes suck like a vacuum cleaner. They don't. So if you replaced the sun with a black hole, we would just orbit the sun as we normally do. So you can orbit a black hole just fine, and then as you get near the event horizon of a black hole, physics gets very weird with time dilation, gravitational redshifting, and very large tidal forces. So